Welcome back. Today we will discuss some more problems related with electric flux and how to calculate it. Basically, how to apply Gauss Theorem. We know, according to Gauss Theorem, the total electric flux through a closed surface E dot ds, this is equal to the charge enclosed within that closed surface divided by epsilon naught. However, make it a point that this way of calculating electric flux is valid only when the surface is closed. If the surface is not closed, for example, some area placed like this in a region where there is some electric field existent, in that case, flux should be calculated as E dot ds. For example, in the diagram shown, electric field direction is in this direction and the area has been held perpendicular to the direction of lines, perpendicular to the direction of field lines. But area vector itself is perpendicular to the surface. Therefore, the ds vector is along the electric field. Therefore, in this case, total electric field will be E ds cos 0, which simply means electric field into ds. That means if area is held, the surface is held perpendicular to the direction of field lines, then the total electric flux is simply the multiplication of electric field and the total area. However, it may not always be inclined in a perpendicular direction to field lines. In that case, you need to find out the angle between the electric field and the area vector. Only then you can find out electric flux. For example, in this case, had the area been held like this, the same area, but it is held, instead of being perpendicular to field lines, it is held at some angle. What you will do, you will find out ds and its angle with the field lines. The total flux would be E ds cos theta. This we have done already in our previous lectures. I will discuss two more cases where the field is, where the surface is enclosed, surface is closed in nature. How would you do that? Let's say there is some electric field existing in a region and a cylindrical surface, closed cylindrical surface. This means that the caps are there and the curved surface, all of them putting together, making it a closed surface is there. What is total flux through this? Let's say its radius is r and its length is L. We know that its total surface area can be calculated as 2 by r into L, that is the curved area, plus twice the area of the caps, which is 2 times pi r square. This is the total area. Now how do you do the electric field through this cylinder? The total electric flux in this case, you can guess it. The total electric flux through this cylinder due to this electric field is 0. It is because the number of lines which enter this surface, they also leave this surface. And as per Gauss Theorem, there is no charge enclosed within that cylinder. So you can put Q equal to 0 over here. The total flux, which is integration of this E dot ds over a closed surface, equaling to Q by epsilon naught, but Q is 0, so total flux is 0. You can generalize this case now. What if in this case the cylinder is not the one with uniform cross section? You may call it an annular cylinder, annular section, or whatever we should call it, a cone with its apex cut out. What is the total flux through it? Oh, it's still 0. Why? Because there is no charge inside this closed surface. Okay, forget about this. What if the field is non-uniform? Now think of the problem and something like this. Now both of them, the closed surface is non-uniform and even the electric field is non-uniform. How would you find out total flux? Oh my god, this is still zero. Simply because Gauss theorem says what is the total charge enclosed within the surface? The answer is the total charge enclosed within the surface is zero, therefore total flux is zero. But it's not that you can apply Gauss theorem always only on closed surfaces. It is valid for closed surfaces, but that can help us to find out electric field even when the surface is not closed, for example. What is the total flux? Let's say, first of all, again consider a closed rectangular cube and total charge Q is placed at its center. What is the total flux through this, all the faces of this cube? Now that's a closed surface and we know that phi is equal to Q by epsilon naught. But what if I am asked to find out electric flux only through its top surface or one of any of 6 surfaces? I know that it's a symmetric problem. Total flux through all these 6 sides is Q by epsilon naught. So flux through this one top side would be 1/6 of this. This will be 1/6 of Q by epsilon naught. You can apply this to many more cases. For example, there is a charge Q placed at the apex of a cone such that this cone is making a solid angle at its apex equal to, say, whatever, pi by 2 steradians. What is the total electric flux through this cone? We know that the total flux, had it been a complete sphere, that would have created the total flux through that sphere. Had there been a complete sphere, the total flux phi would have been Q by epsilon naught. But that flux is passing through the surface area which is subtending a total solid angle of 4 pi steradians. Now it's a simple unitary method question. If total solid angle subtended is 4 pi steradians, the flux is Q by epsilon naught. And you may write it down like that. If solid angle is 4 pi steradian, the flux is Q by epsilon naught. Had the solid angle been 1 unit, the total flux would have been Q by 4 pi epsilon naught. And had it been, in this case it is given to be pi by 2 steradians, then the total flux, let's say I call that phi dash, that will be equal to Q by 4 pi epsilon naught into pi by 2. Now it can be solved easily. It is equal to Q by 8 epsilon naught. So these kind of problems are quite common in flux and application of Gauss theorem. You should practice more of them. One more question I wish to discuss, that will be as an assignment for you. I hope you will solve it out and give me, and you will post the solutions. Let's say we have already using Gauss theorem solved out electric field due to a uniformly charged wire. We have already done it for a spherical shell which is empty from within. All the surface is all the charge is only on the surface. There is no charge inside it. The case may be of empty shell or charge in empty shell, or that of a conducting solid sphere, because in conducting solid sphere all the charge resides on the surface. That also behaves just as if it's an empty shell as far as electric field is concerned. Now in this case, and then we did a solid sphere which is obviously made up of dielectric material such that the charge is residing inside it. We have solved these cases. Can you do electric field due to a hollow cylinder with charge residing only on its surface. Now again, there are two possibilities. Either it is hollow from within, or the cylinder is solid but made up of conducting material. But this cylinder is of infinite length, so there is no chance of charge getting accumulated on the caps. That means charge is only on the curved surface. Can you find out electric field at this point? That means outside the cylinder, on the cylinder, and some point inside the cylinder. You will get quite similar results as you got for shell. And then again you can do one more thing with it. If this cylinder is solid from within and charge is uniformly distributed throughout the bulk of the cylinder, I expect you to find out results similar to that you obtained for a solid sphere. And again, outside the cylinder, on the cylinder, and some point inside the cylinder. These are a few problems which you discuss.